Thank you very much. Thank you very much for the organizers for doing such an excellent job so far, and thanks for inviting me to give this talk. So this is joined with Kevin Hay, who was a postdoc at Caltech and is now at UPenn, and with Fedor Sandomirskiy, who will be a postdoc at Caltech. He was in the Technion and is now moving to Caltech. So here's the talk plan. I'm going to jump right into the model, right into the math. After that, I'll give you some context and motivation, and then I'll tell you about some of our results. This is a very, very preliminary project, so I would be glad for any comments or thoughts. Our motivation, I think we need more motivation for this question. We like this question because it's neat and there's interesting math. Maybe I'll convince you there is some interesting economic motivation, but I think we need more. I'd be glad to hear any thoughts that anybody has. Okay, so here's the model. It's very simple. Finite set of agents, a binary state of the world that's either low or high. All the agents.
If you can slide, we don't see a new slide, Omer.
You don't see the new slide?
At least I don't.
Oh.
No, we don't. It's still a private slide.
Say that you thought you changed slides, but you didn't.
Do you see it now?
No?
No?
Sometimes if you share before you, or if you do things in the wrong order, then it gets stuck on the title slide.
How's this?
Good.
Now it's okay.
Okay. Finite set of agents. Let me.
Can you? Okay.
Almost so far it's the same as my talk tomorrow.
Okay, I think many talks will start like this, right? It's not this is narrowed down to a few tens of thousands of papers, maybe now thousands of papers, still thousands of papers, a common prior. Each agent has private information, some SI, some signal, and there's some joint distribution of these of the state omega and these signals. So far I've really said very, very low. And here's some examples of this. This is just a model of what is private information. And I'm restricting to a binary state and to a common prior. What are some examples? Say public signals. All the signals are the same. Very common choice is conditionally independent signals, which just means that the S's, the signals, are independent conditioned on omega. Now note that these are both examples of private signals, but actually public signals, there's nothing private about them, right? And in fact, even these conditionally independent signals are not so private. So what do I mean by that? Imagine that the prior over the state is a half-half, and that the signals are conditionally independent. They're binary, and they're correct with probability 3/4, right? So when I hear my signal, I know that the state is either high or low, depending on my signal, with probability 3/4. So before agent one observes their signal, they assign belief 1/2 to the other person's signal or type being high. But after I observe, say, my own signal being high, now I revise my belief about the other agent. So now I assign higher probability to the other agent having a high type or a high signal. So in fact, S1 contains information about S2. So these signals are not completely private. They contain information about each other. Okay? So there's not really privacy here. So what is private information? What are private signals? So the definition is very simple. I'm going to say that an information structure, omega and the S's, is a private information structure if the signals themselves are independent. Okay, so this might ring a bell to Itai Arieli and Yaakov Bobichenko were here, and that is because we've in a previous paper with Itai and Yaakov and Fedor, we studied these things. There's not a lot of literature about this. There's maybe one more paper that we found in the statistics literature, but that is the extent of my literature review. So I don't know many, but I'd be glad to know if other people have looked at these sort of things. So what are private signals or private information sources? It just means that they contain information about the state, unless they're trivial, but they do not contain information about each other. When I see my signal, that tells me nothing about your signal. Another way of saying this is that higher order posterior beliefs are trivial. They're equal to the prior. When I see my private signal, it doesn't change at all what I think about your private signal, about your belief also. Okay, so here's some motivation. The first one is a consulting company that sells information about the state. So there's some omega that's interesting to people, The consulting company has information about this and it tries to sell it to different people. But the customers of the consulting property are competitors. They're competing with each other. And the consulting company wants to avoid giving customer information about each other, which would maybe complicate the game or whatever it is that they do next. So the consulting company sort of guarantees when you buy information from it that nobody else knows anything about the information that you have. Here's another motivation. Imagine that this state omega is borrower creditworthiness. So this is whether somebody's going to return a mortgage or not. And S1 is agent 1's type. So agent 1 is the one who's borrowing the money. And S1 is agent 1's type. And this is some private or protected trait, whether this person is a cancer survivor or their gender, or their race, or whatever. And it is correlated with creditworthiness. Now, there's some rating agency that the bank goes to, and the bank asks the rating agency, what is the creditworthiness of this person? Tell me something about it. And imagine that the rating agency, they know omega and they know this protected. They have all the information, and they tell the bank something, some signal S2. Now, this S2 should be informative about the state, about omega. The bank is paying information for that, is paying money for that. But legally, it has to be independent of S1. I cannot reveal to the bank any information about this private or protected trait. So the idea again here is that both S1 and S2 contain information about omega, but they're independent of each other. So this is again would be private information. Now, these sort of private information structures also arise in information design, sort of endogenously, and I'd be glad to hear if maybe Dirk or others have ideas about more connections.
Can I ask a question?
Of course.
So the fact that the rating agency knows S1 is immaterial because it cannot send a signal that is conditioned on S1. The distribution of the signal can depend only on omega, not on S1.
Well, it's more subtle than that. It has to be independent. Well,
Statistically independent.
It's a good question, but you'll see in a minute that that's not exactly the case.
Okay.
You'll see in a minute that that's not exactly the case. S2 has to be independent of omega. Okay, you'll see. That's a good question.
Even with only S1 and S2. When you have S3, things get complicated.
No, just two agents. Yeah, and I think throughout this talk, if you limit yourself to imagining two agents, you will not be missing anything.
Okay, I'll wait.
Okay, so here are some questions. What private information structures are even possible? Is it possible at all to have this? I mean, it sounds sort of paradoxical. How can we both have information that's correlated with the state, but our signals are not correlated with each other? And this has been addressed in the literature already. The more interesting question is, how informative can they be? Is there some limit to how informative signals can be if they're independent of each other? And the answer is yes. And we're going to see some simple examples of this. We're going to talk about a notion of Pareto optimal private information. Because there are limits to how informative private signals can be. Maybe I should call them PP signals for short. But because there's a limit to how informative PP signals can be, maybe I'll stick to private. Because there's a limit to how private signal, how informative they can be, they're going to be Pareto optimal ones, where you cannot make them more informative without giving up this property of being private. And then we'll talk about this example that I said above. How do you design optimal signals under privacy or equity constraints? Okay, so first, let me show you an example of private signals. So what I have here is can you guys see my mouse? Yeah, okay, so what I have here is the unit square in R2. And here's how I'm gonna choose omega and the signals. When omega is high, I'm gonna choose the signals from the uniform distribution over this blue triangle. When omega is low, I'm going to choose them from the uniform distribution over the white triangle. Now, overall, if the state is half-half, the joint distribution of S1 and S2 is just the uniform distribution over the unit square. So S1 and S2 are independent of each other, but they do contain information about the state. For example, if agent 1 is told that S1 is 0.9, they in fact assign probability 0.9 to the state. So in fact, in this case, this SI is equal to the posterior that it induces. After I see a signal SI, that's actually my posterior that I'm told. So when I get a high signal, I'm pretty convinced that the state is the high state. When I get a low signal, I think it's the low state. And still, I know nothing about the other person's signal. Condition on my signal, the other person's signal is completely independent. Let me show you a different example. So again, I'm going to do the same trick. When the state is high, I pick uniformly from the blue area. When it's low, I pick uniformly from the white area. Again, then the signals are just independent, uniform on 0, 1. In this case, see what happens here. When my signal, let's look at agent 1. When the signal is somewhere over here, the probability that I assign to the high state is 1/4. Here also, the probability that I assign to the high state is 1/4. Here and here, the probability that I assign to the high state is 3/4. So I do get a real number between 0 and 1, but in terms of the beliefs that it induces, there are just two options. With probability 1/2, I get belief 1/4. With probability 1/2, I get belief 3/4. And same for the other player. And these are truly independent signals, again, because they're just distributed uniformly on 0, 1. So these signals are equivalent in terms of the belief that they induce to just a 3/4 binary signal, but they're completely independent. So both agents get this 3/4 binary signal about the state, but they learn nothing about the other agent's signal. Here's another example, and these are now 2/3 binary signals. And this is just a hint that actually it's not so simple to construct. How do you exactly generate these signals in a way that's completely independent? So there's some interesting stuff going on here, but I'm not going to be able to go too deeply into that. So here's some formal definitions. I'm going to look at two private. Yes, you have a question?
Yeah, I'm just wondering. So about the general construction. So if I think of omega as a Cartesian product of two omega 1 and omega 2, and S1 gives me information about omega 1. Omega 1 and omega 2 are independent, and S2 tells me something about omega 2. Does that cover all the cases? So in your example, omega 1 and omega 2 will be kind of the XY axis of omega.
I'd have to think about that. But here we're focusing on just binary omega.
I can represent, omega 1 and omega 2. I can, this is a mapping which is binary. Right? I don't. It doesn't have to be the full number in the 0, 1. It just has to be a mapping from that.
Right. So sorry. Yeah, I'm with you. So in fact, we'll see that without loss of generality, you can take omega 1 to be the interval 0, 1, omega 2 to be the interval 0, 1, and so on. Okay, so you'll see in a second. Sorry.
You mean S1 and S2? You mean S1 and S2, not omega 1, omega 2.
Also omega 1 and omega 2. So you can imagine that the real states are just the signals, and the state of interest is some function of the signals, some deterministic function. So I'll talk about that in a second. Okay, so we're going to have two private information structures, S and T. And I'm going to say that S, Pareto dominates T, if from the point of view of each agent, the signal SI is a signal over omega, dominates TI. Okay? And I'm going to say that S is equivalent to T if they dominate each other, which just means that from the point of view of each agent, it doesn't matter whether they get SI or TI, they're Blackwell equivalent, which also means that the posterior distribution induced by SI is the same as the posterior distribution induced by TI. So the equivalence classes here, and we're only going to be interested in things up to equivalence, is just what are the distributions of posteriors of each agent. And I'm going to say that S is Pareto optimal if every private information structure that Pareto dominates S is equivalent to S. So there's nothing that strictly dominates S. So this is sort of the usual notion of Pareto optimality, or the Pareto frontier, or Pareto efficiency. Okay, but the important part is that this is just from the point of view of each individual agent. You cannot make all agents happier by giving them all Blackwell dominant signals. So that's what it means for a structure to be Pareto optimal. Okay, so now let me give you a representation theorem. And here's the generic way to construct a private information structure T. I'm going to choose, just like I did until now, some measurable subset of 0, 1 squared, or more generally 0, 1 to the n. So on the right here is what I chose before, but you can take the one on the left here. You should ignore the black circle. It's just the blue part. And when the state is high, I choose T uniformly from the set A, from the blue set. When it's low, I choose from the complement. And I'm going to call T the structure associated with A. And the proposition is that this is everything. You can, up to equivalence, you can construct everything this way. So whenever you have a private information structure S, there's going to be some measurable blue subset like that, such that the associated structure is equivalent to S. So as long as I'm only interested in things up to equivalence, and remember, equivalence just means that it induces the same posteriors in the agents, I can just assume that this is how I construct information structures. Okay. Private information structures. Okay, so now I'm going to be interested in these Pareto optimal
Sorry,
things.
and Omer, this statement is now true for the binary state space, or
Yes.
more
This is
general?
I can't see who's asking this, sorry.
That's Dirk, sorry.
Dirk, sorry. This is for binary state space. We
Great.
have not looked too deeply into larger state spaces yet.
Okay, great.
I'm a bit confused, Omer. Does it mean that knowing all signals, you know omega?
Yes, you can, without loss of generality, assume that if you know all signals, you know omega. Exactly. That's equivalent.
How is that? I mean,
Well,
for example, non-informative signals.
Well, here, I can give you a bit and me a bit, and let the state be the sum mod 2 of these bits. Then these are completely uninformative about the state, but together they reveal the state.
No, I understand, but something is bothering me. Suppose S1 and S2 are completely non-informative. They're independent of omega. So I know S1, I don't know anything about omega.
No, but I'm saying they will be equivalent. These are equivalent to a structure, which I just described, in which both signals are completely uninformative, but they reveal omega. So this is up to equivalence. I have 5 minutes, so let me move on and we can discuss this. Or maybe I have 10 minutes because we started 5 minutes late. I'll let the organizers decide. So here's a question. Here's something maybe unrelated. It's a problem from tomography. And we're going to have some subset of, say, 0, 1 squared. And what I'm going to do is I'm going to measure the density of the projection of this subset on each axis. So imagine that I'm shining an X-ray from left to right and from up to down, and I'm seeing how much gets through at each point, which tells me what is the density of each line that goes through the shape. And I'm going to say that this shape is a shape of uniqueness if this projection information determines A exactly. And this is sort of what happens in a CAT scan. That's why this is related to tomography. Maybe there's more than just 2 directions in a real CAT scan, but this is the idea. Okay, so is it clear what I'm doing here? I'm projecting this shape as a measure, as the conditional measure. I take the Lebesgue measure, condition on the shape. I project this measure on the 2 axes. I tell you that these 2 projections and ask you, can you tell me what the shape was? And if the shape is a shape of uniqueness, if you can reconstruct, if these 2 projections determine the shape. So here's the theorem. The information structure associated with a set A is Pareto optimal if and only if A is a shape of uniqueness. And what do we know about shapes of uniqueness? Well, in 2 dimension, A is a shape of uniqueness if and only if, again, up to equivalence, it's upward closed, like the example here on the left. The 2 examples on the right are equivalent. So these are not shapes of uniqueness. This is this 3/4 binary signal. You can see that if you look for a second, you see that the projections on both axes are the same for these 2. They're these 1/4, 3/4, which means that this independent binary 3/4 signals do not represent a Pareto optimal signal. I can give people even more information while preserving independence. The one on the left, because it's upward closed, is Pareto optimal. There's no way to add more information without giving up this independence property, this private information property. And unfortunately, in more than 2 dimensions, it gets much more complicated, and we don't know of any good characterizations. Okay, so the last thing I want to tell you is a little bit more about this private protected information question. So again, imagine that
when you say, Omer, just understand, when you say permute the axis, you mean you rotate the axis, not permute. It's not exchanging x and y, but deciding what is positive and what is negative.
Well, you can apply a measure preserving transformation to each axis. That doesn't change.
Yeah, because otherwise, again, I could take the triangle like this, which is not upper closed, and that will also be okay.
You're right. This is not a good phrasing. It's not changing the 2 axes. It's on each axis, apply a permutation or a measure preserving transformation.
Okay.
The big measure preserving. Okay. So just let me end with this. So we have, let's go back to this privacy and protected information question. We have omega, which are a state of interest, and some S1, which is some private protected characteristic. We're going to fix their joint distribution. And we want S2 to be informative regarding omega, but independent of S1, right? So I want to tell you something about the state, but I'm not allowed to reveal any information about S1. And the question is, what is the most information that I can give you? Which is related to the question, can we choose S2 to make this triplet Pareto optimal? Now I'm going to denote by F the CDF of distribution of posteriors induced by S1. So when I observe S1, F is going to be the distribution of the posteriors that I have. Here's a proposition. There is a signal, S2, that makes this Pareto optimal, and it's unique up to equivalence. The distribution of posteriors that any such S2 induces has CDF F minus 1. This means, so this takes a little bit of time to digest. I don't know if I have time to explain it, but the idea is that if you fix S1 and omega, there is a maximal signal in the black hole sense that I can give you that preserves independence. Any other signal that I give you, any signal that will induce a different belief distribution, will be black hole dominated. So whatever you're going to do with this information, you prefer to get the signal S2 to any other possible signal. There's a unique best signal that I can give you fixing S1. And it's very easy to calculate the CDF of the signal. The CDF of the signal is just going to be the inverse of the CDF of S1. So let me end with an example. Imagine that omega is, say, creditworthiness, and S1 is gender, or race, or disability, or maybe omega is whether a candidate is fit for a position, and S1 is the candidate's age. So omega will be low or high, so the fit or the creditworthiness, and S1 will be X or Y, whatever it is. And let's assume the priors are all, the marginals are all uniform, so you're equally likely to have high or low creditworthiness or to have this trait S1 be X or Y. But these things are correlated. So the probability that the state is high, given that S1 is Y, is 1/2 plus some C. C can be anything between 0 and 1/2, which is the same as the probability that omega is low when S1 is equal to X. It turns out that the optimal signal that I can give you is what's depicted up here. The signal will have 3 values, either low, the empty set, or high. When you get the empty set, you're told nothing. It's 1/2. So you can see when you get the empty set, your posterior is 1/2. The low or high signal is completely revealing. You know exactly what it is. And the probability of getting an unrevealing signal is 2C. So the more correlation we have, the more likely you are to get a completely unrevealing signal, to get a trivial signal. The less the correlation, the more S2 can reveal to you about this state, because it's less correlated with the hidden thing. That's all I have. And I'll leave this picture on here while we're asking questions, just to impress upon you that some interesting things are going on.
Can we get the previous picture? In fact,
Unfortunately,
I know it's nicer, but I want to understand this. So when H, oh, okay, no, nothing. Let me.
okay.
In particular, this is independent of the prior, right?
No, the prior.
Not this one, the previous proposition. The optimal S2 given S1 is independent of the prior?
That is a good question. I have to think about that.
Or is this for a prior of 1/2? this proposition?
No, it's independent of the prior. Whatever the, okay, I'd have to think about that for a second, but I think it is independent of the prior. Okay. I'll if I told you the wrong thing, I'll get back to you on that.
This is somewhat surprising.
Maybe Fedor in the audience knows better and can put in the chat whether this proposition is independent of the audience or Kevin, but I think so.
So if we, meanwhile, okay, if we go back to the other slide, the point is not that you learn nothing about S1, you learn nothing about from S2, you learn nothing about S1 beyond what you know about omega.
No, you know nothing beyond what you knew prior to seeing S2.
Yeah, I mean
you had some prior over S1. After I show you S2, nothing changes in your prior. You had some prior distribution of S2, which without loss of generality, you can take to be the uniform distribution on 0, 1. Nothing changes after that. So I mean, you can see here, this is, the x-axis is S1, the y-axis is S2. The joint distribution is just the product distribution on 0, 1. So after I see S2, I learn nothing about S1. But I do learn something about the state because it's actually revealed to me when my signal is.
But in the state, no, learning something about the state also tells you something about S1 because there is a correlation between S1 and the state.
No,
so you
no,
don't.
No, you learn nothing about S1. So your prior was that S1 is uniform on 0, 1. After you observe your signal, your prior is still uniform on 0, 1. You learned nothing about S1. This is the paradox. I had to go very fast. Maybe I should have been less ambitious, but this is the sort of paradoxical thing here. You learn absolutely nothing about S1, even though you do learn something about the state. Your posterior regarding S1 is the same as your prior regarding S1.
So, Omer, can I make a comment? So I think I'm in the official discussion for the paper, so I feel it's okay if I take a little bit of time. And this is in response to your request for some ideas for motivation. So what I was thinking about is maybe if you're providing information to some customers, and then there's going to be a monopolist who will design a revenue maximizing mechanism, right? And you just want to maximize the consumer surplus. Then you want to give them information about their valuations, but not in a way to create correlation between their signals, because then the seller could use a Cramer-MacLean mechanism. So that's one setting in which this sort of private information could actually be optimal. So to optimally provide information in such a setting, you would want to use these signals, and this characterization could be quite useful because you want to inform the customers about their values, but not to the extent of creating some correlation,
so
even if there's a common value component.
Are you sure that it would be a hard constraint that I would want to have exactly 0 correlation?
So that I don't know, but we know for Cramer-MacLean that generically, whenever there's a little bit of correlation, even right, the seller will be able to extract all the surplus. So I conjecture that you would want to use this private information structure. So just an idea. I have no idea if it's actually going to work, but maybe something worth looking into.
Thank you.
Actually, that's a very nice suggestion, and I think that's precisely the reason why you saw these independent information structures show up in the work with Ben and Stephen, because that is the information structure that doesn't allow us to use correlation and therefore gives the bidders a larger surplus. So that's what pushes them in this direction.
I see. Okay, I should know this literature better. I apologize, but it's good to.
No, you mentioned it.
It's good to learn from the source.
And building on what Dirk and Piotr just said, another thing you might be able to use these tools to look at is rather than providing no information about S2, perhaps you want to try and induce particular distributions over S2. Do you think these tools could be used at all if you wanted to say fix some level of correlation, but maybe not something like conditionally independent signals?
Yeah, that sounds nice.
In order to, depending on the market that agents were operating in.
I haven't thought about that, but that's a good suggestion from referee too.
And also algorithms, if they're supposed to use certain information, which is so informative that nothing else, like the most informative signal you can disclose, conditional on it being independent, is uninformative. So that the S2 that you can provide has to be uninformative about the state if you want it to be independent of S1, then you have to exclude S2 from consideration in algorithms, or you have to exclude S1 from consideration in algorithms, something like that. If S2 has, if
It turns out
S2,
that as long as S1 is not completely revealing, there will be some informative S2 that does contain information.
well, but if it is its precision is very low, then it might not be good for decision making. So perhaps in terms of what data is it optimal to use while preserving some form of privacy, that might be an application, but
Thank you.
while still being useful.
Yep, I see. Thank you.